Hey everyone. So today's video is going to be about the simple hacks that we can use in the volume relationship in the chapters of mole and stoichiometry. Imagine we have a chemical lab where the temperature has been set to 25 degrees Celsius. Now 1 mole of any gas under these circumstances is going to occupy 24,000 centimeter cube, or let's say 24 decimeter cube. That is the same thing, right? Now, it does not depend on the molecular mass or the identity. It is true for any gas, whether it can be hydrogen or water vapors or SO3 gas. We can vouch for the fact that all the gases under the same conditions of temperature and pressure, so under same condition of temperature and pressure, the mole ratio between two or more gases is equals to the volume ratio between these gases. For example, we have an equation between SO2 which reacts with O2 to produce SO3 gas. We balance it and we get to know that 2 moles of sulfur dioxide react with 1 mole of oxygen, 1 mole O2, and produce 2 mole SO3. Now we know that the same volumetric ratio can be applied to 2 volumes of SO2 react with 1 unit volume of O2 and produce 2 volumes of SO3. If it's 10 centimeter cube of SO2 and we want to see how much SO3 is being produced, the ratio is exactly 1:1. So it's going to be exactly 10 centimeter cube of SO3 as well. But with oxygen, the ratio is 2:1. So 10 centimeter cube SO2 reacts with 5 centimeter cube of O2. Simple, right? Now for example, we want to apply different values. 20 centimeter cube of SO2 is reacting in a certain scenario. We want to see how much oxygen is needed in this exact condition. So we know the ratio between SO2 and O2 is 2:1. So between SO2 and O2, the ratio is 2:1. We get to know that if 20 centimeter cube of SO2 is reacting, how much O2 would be needed? And it's simply exactly 10 centimeter cube, because these things work in ratio. We don't have to calculate the entire moles over here. Let's work with a rather complicated equation where 4 ammonia reacts with 7 moles of oxygen and produce nitrogen dioxide and water. Now if there's a question that says 80 centimeter cube of ammonia is reacting, and it wants to see how much NO2 is being produced in terms of volume. So there's a relationship between ammonia and NO2 that we can see. The ratio is very simple. It's 4:4, which can also be said as 1:1. So between ammonia and NO2, the ratio is 4:4, rather 1:1. If 80 centimeter cube of NO3 is reacting, how much NO2 can be produced? It's going to be exactly the same, 80 centimeter cube NO2. Simple, right? No molar calculations. If 80 centimeter cube of ammonia was reacting, and somebody asks me about oxygen, and asks me how much oxygen would be needed over here, then the relationship is between ammonia and oxygen right now. So we know the ratio between these two things is 4:7. So we know ammonia 4 moles reacts with 7 moles oxygen. So if 80 centimeter cube is the volume of ammonia and X is the volume of oxygen, we simply solve it and we get to know that it's going to be 80 times 7 divided by 4. Not 40 obviously. So the volume is going to be really simply 140 centimeter cube. Yeah, that is the answer. So it's really simply 140 centimeter cube without the need of any molar calculations. Let's try one more. 2 moles of ethane react with 7 moles of oxygen to produce 4 moles of carbon dioxide and 6 moles of water. We just, balance it. So we know if 16 centimeter cube hypothetically ethane is reacting, 16 centimeter cube is hypothetical value, and someone asks me how much carbon dioxide could be produced. So there's a relationship between ethane and CO2. It is a relationship of 2:4, Or you can put it like 1 is to 2, right? So 2 is to 4, which can be written as 1 is to 2. We simply find the volume of carbon dioxide using the 16 centimeter cube in the question. Carbon dioxide is obviously going to be twice, which is 32 centimeter cube. So how much carbon dioxide do we get? 32 centimeter cube under the same conditions. Now we know that how these ratios work. Let's try one more. If 40 centimeter cube of ethane is reacting, how much oxygen would be needed? Now this is a rather more complicated ratio. It's a ratio between ethane and oxygen, which is 2 is to 7. It can't be simplified any further. So 2 ethanes react with 7 oxygens. If 40 centimeter cube is reacting of ethane, how much centimeter cube for oxygen would we need? We simply do the cross multiplication and we get the answer to be again a very simple value without the molar calculations. So it's going to be, let me do it, 7 times 40 divided by 2 is going to be 140 centimeter cube. Well, coincidentally, the same answer last time. So I hope these ratios are clear to us. There's a question that says what volume of oxygen is needed to combust 10 centimeter cube of propane? 60, 30, 40 or 50? So propane and oxygen have a relationship which is 1 is to 5. We have the volume of propane, but we don't have the volume of oxygen. So between propane and oxygen, the ratio is 1 is to 5. If 10 centimeter cube of propane is being used, how much oxygen do we need? It's a simple proportionality. It's going to be 50 centimeter cube, so D is going to be the answer. This question says, what volume of hydrogen produces exactly 2500 centimeter cube ammonia? We have 4 options. Between hydrogen and ammonia, we have a relationship. It is 3 hydrogen and 2 ammonias. So let's rewrite this ratio over here. Between hydrogen and ammonia, the ratio is 3 is to 2. What volume of ammonia do we have? It's 2500 centimeter cube. What volume of hydrogen do we have? We don't know. So let's simply solve it. We're going to get the answer of 2500 times 3 divided by 2, which is going to be 3750 centimeter cube. Even with such larger values, we can simply get the answer. So I hope things are getting clearer to you. Let's pick on the idea that whenever we have such scenarios, we do the same working every time. For example, the mole ratio in this scenario was given to us through the equation, and the volumetric ratio we developed. So mole ratio and volume ratio are same. We don't have to do the entire calculation for 1 mark questions or MCQs. We can simply use this value and we get the answer, where we put the volume on one side of the fraction and the mole ratio from the other side of the equation. And it is applicable to all gaseous equations. Mole ratios, right? So I hope